Hey everyone, and welcome to The Explainer. Today, we are embarking on a deep dive into a truly paradigm shifting paper that is honestly fundamentally changing how we understand brain function. We're moving way beyond the traditional ways of looking at brain activity and stepping right into the fascinating world of neural timing. So get ready, because the way you think about how your own mind works is about to get a major upgrade. For decades, when we've thought about devastating conditions like Alzheimer's and Parkinson's, we've largely focused on the physical deterioration, right? The loss of neurons, the breakdown of anatomical connectivity. But what if that is only half the story? What if there's this crucial missing puzzle piece sitting right in front of us? What if these disorders are actually just as much about the brain losing its internal rhythm, its ability to keep time?
Okay, let's dive into this. Section 1. Beyond traditional brainwaves.
To really grasp this breakthrough, we first need to look at how we've traditionally viewed the electrical activity in our heads, and why scientists are suddenly realizing we need a totally new approach. Think of your brain like a massive symphony orchestra. Traditional electrophysiology, using standard EEG to look at oscillatory power and event-related responses, is kind of like just measuring the overall volume of the orchestra, or maybe checking how loud the string section is compared to the brass. And hey, that's incredibly useful. But it misses a absolutely critical layer of organization. That is where transient integration events come in. This is all about the moment-to-moment formation of coordinated neural states. It's not just about the volume, it's about the precise rhythm. It's about the exact literal millisecond those musicians play together to form a complex chord. Because without that precise timing, you don't get a symphony, you just get noise. Which brings us to Section 2, introducing the neurobyte.
So this is the big shift toward a brand new metric called the neurobyte. Basically, these are brief periods of elevated, coordinated neural activity identified through envelope-based EEG analysis. Rather than focusing solely on oscillatory magnitude, just how big the brainwaves are, these neurobytes actually capture the timing architecture of neurocommunication. They isolate those exact, fleeting moments when distributed neural populations sync up and coordinate their activity to process information.
Now, what's really interesting about this slide is how the electrical Pierre-Gentil, or ECEPJ framework, grounds this whole concept. It takes a highly abstract idea, the actual timing of a thought, and gives it a defined operational marker, the neurobyte.
So let's look at how they did it. Section 3, Testing the ECPJ Framework.
It's a brilliant theory, for sure. But how do we know it's real? How do researchers actually prove they can reliably measure this timing architecture? Look at that number, 109. That number is incredibly important. It represents the 109 healthy participants pulled from the publicly available PhysioNet EEG dataset. If you want to prove that you can measure the intricate timing of the human brain, you can't just look at one or two people in a lab. You absolutely need a large, population-level scale to establish a rock-solid baseline of what healthy neural timing actually looks like. And this wasn't just simple baseline data. The dataset parameters were rigorous. We're talking 64 individual EEG channels across the scalp, recording multiple runs of both motor execution tasks, like physically moving hands and feet, and motor imagery tasks, where subjects simply imagined moving them. This gives us a rich, highly dynamic picture of the brain actively working and coordinating. To find the neurobytes hidden in all that raw data, the researchers used a standardized MNE Python preprocessing pipeline. Think of this like a highly specific sieve. First up, they applied a bandpass filter between 1 and 30 Hz. Then, they zoomed right in on a specific region of interest, the motor cortex, specifically isolating channels C3, CZ, and C4, because those are central to motor execution and imagery. Finally, they applied a Hilbert envelope transformation. Actually, to put that simply, it's basically a mathematical way to smooth out the jagged static of the signal so we can easily trace its overall energy and shape. But wait. How do you separate a true moment of neural coordination from just a random blip? Well, they established strict neurobyte candidate criteria. The signal's envelope Z-score had to be greater than 1.8, and the event had to last between 30 and 500 milliseconds. These specific thresholds are vital. They ensure the researchers are capturing real, physiological bursts of coordinated activity, purposefully filtering out isolated noise or events that drag on so long they completely lose their transient nature. Let's look at what they found. Section 4, Measuring Neural Timing. And this brilliantly illustrates the results, the actual quantifiable metrics of human thought timing extracted from those 109 brains. The analyses generated super consistent measures. We have event count and density, literally telling us how many of these coordinated bursts happen per minute. We have mean duration. And crucially, we have the mean inter-event interval, or IEI, which measures the temporal gap between these events, along with IEI variability, which shows the temporal irregularity. So they didn't just find these neurobites, they mapped the specific temporal structure of how the brain operates from moment to moment. So the crucial point to take away from this is, across all 109 subjects, these neurobite events occurred repeatedly and reliably. By successfully extracting these metrics across a large group, scientists have now established a normative reference framework. We finally have a standardized benchmark for what healthy neural timing is supposed to look like. Now let's look at the other side of the coin. Section 5, the disease connection. We have the healthy benchmark, but what happens when things go wrong? When we look at neurodegenerative conditions like Alzheimer's and Parkinson's disease, the human impact is devastating. But armed with this new perspective, researchers hypothesize that the core issue may not just be structural. The brain's timing architecture itself may become disrupted and fragmented. The orchestra's instruments are slowly falling entirely out of sync. Let's move to this and see how it builds. Contrasted against the healthy data we just talked about, pathological timing disruptions manifest in very specific, measurable ways. We might see reduced neurobite density, fewer coordinated bursts happening overall. We might see increased inter-event intervals, meaning much longer, sluggish gaps between coordinated thoughts. We'd see greater IEI variability, pointing to highly fragmented and irregular integration dynamics. This is the massive aha moment of the explainer. From this perspective, neurological disease may be viewed not only as neuronal loss, but as a progressive deterioration of timing architecture. It completely reframes how we look at these diseases. We are no longer just looking at a loss of hardware, we are looking at a fundamental corruption of the brain's timing software. Wrapping up with Section 6, the future of brain health. So where does this lead us, and what hurdles remain? To be absolutely clear and impartial, the researchers outlined some specific limitations. The ECPJ framework's Neurobite is currently an operational, EEG-derived construct, meaning it definitely requires further biological validation. Also, this foundational study only looked at healthy participants, so disease sensitivity hasn't been clinically established just yet. The detection thresholds might need to be optimized, and future work will need to include things like phase synchrony and source localization to get an even clearer picture. But make no mistake, the foundation is now built. Which leaves us with this final remarkable question. We've learned that brain function depends heavily on the precise temporal organization of neural integration. If neurobites give us the tools to finally bridge electrophysiology, cognition, and neurological disease by measuring this timing, the implications for future treatments are staggering. If we can measure the broken rhythm of the mind, how might we one day learn to tune it? Thank you so much for joining me for this explainer, and keep questioning how the world and your mind works.